Hi, my name is Yaman Bhati and I'm here today to present a presentation on the topic CTOD test of high strength steels. What is CTOD test? It stands for crack tip opening displacement test. Now I'm going to talk about what crack tip opening displacement test is. Firstly, we take a specimen which we need to measure or we need to test. And that specimen is a crack is induced in the center of the specimen first, and then it is placed between 3-point bending apparatus that is shown over here. Now the center point over here is used for loading. It gives a constant loading for a long time, and the crack keeps opening and opening till the specimen actually breaks. Now what we are doing here is we're trying to find the resistance of that material to the crack propagation according to the load applied on the specimen. Now there's a clip gauge you can see over here, which is actually used to measure the opening of the crack. Then once we have loaded it and then the crack keeps opening, we plot the graph between the load and the crack opening. This is how we do CTOD test. Next, I'm going to tell you why CTOD test is done. CTOD test is done to find the resistance of the material to the crack propagation, which, for example, if we have any structure which a crack generates in a structure somewhere in the steel specimen or any kind of place, and we need to find that how much time will it take for that crack to propagate as so much that the structure literally fails but due to the load. So that's why we do this crack tip opening displacement test to find the resistance of the crack propagation of the material. Now secondly, we are able to tell the toughness of the material due to CTOD test. Thirdly, this CTOD test is only done on materials which show plastic deformations. No other material can be subjected to CTOD test because they'll immediately break. For example, in case of brittle materials, if they're subjected to a fracture opening and then subjected to the load, they'll immediately break. They'll just crack open. And as I talked about, these CTOD test is done so that we can find the material's toughness and the resistance to crack propagation so that it can be used for construction in steel structures like mega structures, bridges, buildings, anything you can think of. Next, we can see that there are new methodologies that have been brought up into the CTOD test. Like some researchers have used in situ stage, some have used maximum crack opening displacement, and some have used small punch test. These are the new things that have come up into the CTOD test, the basic CTOD test that we talked about earlier. Now, since my topic is CTOD test on high strength steels, I'm going to talk about high strength steels. High strength steels are generally steels that have very high toughness compared to normal steels, and they have corrosion resistance. They have resistance to crack opening, so which is they'll have a very high CTOD value, of course, if subjected to CTOD test. And these high tensile, and they have high tensile strength as well. And these steels are nowadays used in mega structures like building bridges and everything. We all earlier talked about why CTOD test is done. It is done because we can tell about the toughness of the material. But now what I've focused on is how to improve the toughness of the material so the CTOD value increases. That's the main thing. If we need to meet the requirements of the structure, steel structures being able to withstand the load nowadays due to big vehicles and everything, so we need a greater toughness for those steels. Now, the thing comes to the mind is how do you improve the toughness? I have researched through a lot of papers and I have seen a lot of different ways that the researchers have tried to increase the toughness of the steel. Some of them are mentioned here. For example, there's heat treatments, which increases the toughness of the steel, laser quenching, cold working, and addition of materials to be used. Now, additional materials to the steel was what intrigued me. You can add something into the steel so that it becomes very strong. And it increases CTOD value, that is the resistance to the crack propagation of the material increases due to an addition of any kind of material to the steel specimen. So there was a research that I studied about was addition of TIN-MNS steel, that is two steel, sorry, and that is there are two types of steel, S and N. The composition is given in the table. These two steels were vacuum melted and rolled together into thick plates of 50 mm. The new steel that was formed due to the thermomechanical control process had a tensile strength of 490 megapascal. Now that's a lot of strength. So that actually was very good. But the thing is that during this research, they only focused on impact test, that is CTOD test and CHARPy test. What I wanted to focus on, like whether it can sustain fatigue testing. And the reason for that is because there's a lot of fatigue failure in cold temperatures. Now, why there is fatigue failure in cold temperatures? Because when steel is open to cold temperatures, like when the temperature go below -30, goes to -40, -50, the the composition of steel starts to change. The temperature decreases, and the steel changes from ductile to brittle. And if there's brittle, then cyclic loading will actually cause it to fail in steel structures. So I was thinking that maybe we can use this thin M&S steel so in building steel structures or bridges in cold temperatures, if it can sustain the values, it can sustain the fatigue testing and generate enough satisfactory values. Now, my research question was that, and I'll read out the research question now. The research question is to determine whether the utilization of TIN-MNS complex precipitate in the specimen of steel can generate enough resistance to fatigue failure and crack propagation in the heat affected zone of the welded steel, so that this specimen can be used for the construction of steel bridges in cold temperatures. Now, why welded steel? Because in while building bridges and everything, you have like welding done between the steel specimen, so the toughness has to be created in the welded zone as well. Now, my research design was actually about experimental design. Like, I'm gonna use a lot of specimen, do experiment on them, and I'm gonna define how the stepwise how my experiment goes. Firstly, I will use the same method the other researchers have used, is like forming the thin M&S steel. Thin M&S is titanium nitride manganese sulfide steel. So they're like titanium nitride steel is separate, manganese sulfide steel is separate. Those two are combined together, using rolling process and vacuum melting, and then using the thermomechanical control process, a new type of steel is formed which has a very high tensile strength. This is the steel that I want to do the fatigue testing on. Now, I would like to do the fatigue testing at -50 degrees Celsius, so that it takes the temperature, like it considers the minimum temperature that could go while in the real life conditions where the steel structure is made or the bridge is made. Now, I'll be using 6 different specimens with different dimensions, like 10 mm by 10 mm by 5 mm, or 10 mm by 10 mm by 10 mm, and so on, like 6 different specimens. Each specimen of its own dimension will be welded together, and the fatigue testing will take place on it. Now, the welding that I'll be using to weld those will be together will be shielded metal arc welding. This is the most common type of welding used in bridges. That's why I'm using this, so that my results could be very close to the real life conditions where the steel bridges are constructed. And heat input that I'm using is high heat input, that is 20 kilojoule per mm. And the fatigue testing will be done in there will be 200,000 cycles of load of 850 kg per mm on the specimen, so that we can be sure that it can generate, it can sustain the load due to the vehicles on the steel bridges, or if you're constructing any type of buildings, it can be used there. Now, research design. Now, the strengths of my research design is actually I'm using multiple specimen, so I'll get accurate results. I can tell out of all those specimen that which is the best that can be used to construct steel bridges, what dimension specimen that I can use, which was better in giving results compared to the load that was put on it, and the number of cycles that it went through during the fatigue testing. Then that'll be it'll come, if my research is successful, I'll come to know that the titanium nitride manganese sulfide steel is strong enough that it can resist the fatigue failure at cold temperatures, and that can be used in the construction of steel bridges in the cold temperature regions, such as North Dakota, for example, in the United States, where the temperature drops up to -40 degrees Celsius. But the limitations, my research design has limitations as well. The limitation is that it does not account for real life conditions. For example, I am doing the fatigue testing, but in a controlled environment. The temperature is -50 degrees Celsius. It is constant temperature. There's no wind, there's nothing. So I'm not really sure that when we actually build the bridge in the real life conditions, how the temperatures, how the surrounding will affect our steel bridge. Any questions? Thank you very much.